Question carefully. I'm not saying that it has a bad effect on cholesterol. I'm saying that suppose it had no effect on cholesterol, what's the probability that this happens? So let's look at this. So if diet has no effect on cholesterol, then there is a 50-50 chance, or there is a p equals 1/2 probability that a person on this diet has a lower cholesterol content.
That's true.
Yeah, I'm kind of confused on why it's a half of a probability if it doesn't affect it at all.
It doesn't affect it, so that means, so if you don't do anything, on any particular day, your cholesterol can be lower or higher, right?
Okay.
So it has no effect. I'm not saying it has a bad effect on cholesterol and then, oh, it's gone up. I'm saying it has no effect. Then one of two things can happen, right? Either your cholesterol can go up or it can go down. Okay, I'm discounting the case that it stays the same. I'm taking the case that it stays the same as including it. Say the probability that this particular thing happens is 0. Okay. So either it goes up or goes down, and if it has no effect, it's not pushing it in either direction, right? So either direction is equally likely. It goes up or goes down.
So just based on your body, pretty much?
Right, yeah.
Okay.
So this is just like sort of, the effect of that is like the effect of noise, as you say. It's just sort of, it's not pushing it in any particular direction. It's just random. So if something has no effect and there are only two possible outcomes, okay, and it doesn't affect it doesn't favor any one particular outcome, then the outcomes are equally likely, right?
Okay. Yeah.
So I'm saying that this has no effect at all. So you basically toss a coin and say, okay, either your cholesterol is high today or it's low. That's it. All right. Okay. So say with stress, your cholesterol can go up. So maybe stress causes it to go up. You're not stressed, it goes down. So that is what basically is determining. It's some random noise that just makes it 1/2 that you can go up and down. All right. So this is no effect. I'm not saying that this has a detrimental effect. If it has no effect, then this is a reasonable assumption to make. There's 1/2 probability that it will. All right. So we have one probability that it lowers this thing. Low cholesterol reading after this experiment. So we are interested in what's the probability that this happens, that the nutritionist endorses it, although it doesn't. P is not greater than 1/2. P is just 1/2, and still the nutritionist endorses it. So this is if X. Where is it? I didn't tell you what X is. So here, let X be number of people with lower cholesterol reading. So probability that exactly the number of people is greater than 65% of 100, so that's the 65. It's then equal to 65. So in this case, so if this diet has no effect, then X is just binomially distributed with n equals 100 people, and they fall into the category with low cholesterol with probability 1/2, each of them. All right, so so under this assumption that it has no effect, your X has this distribution. Supposing if you believe that it has some good effect, then this P would be something large. Our initial assumption would be P would be something large. But if it has no effect, then P is just 1/2, and then what's the probability that X is greater than or equal to 65? All right, so probability X greater than or equal to 65, that's a probability that X takes 65 to 100, that's going to be 100 choose X, 1/2, X, 1/2 to the 100 minus X. So again, just hoping to get this 1/2 to the 100. So of course we're not going to do this calculation, no one wants to sum these many numbers. So what we're going to use is a normal approximation to binomials. So whenever you're dealing with large numbers, right, you definitely want to use normal approximation, just because it's more convenient. So we will use normal approximation. What's your NP value? It is 50, right? 100 times 1/2. What's NP1 minus P, or variance value? 25. The probability X greater than or equal to 65. At this point, we're doing a normal approximation to binomials, so we've got to first of all do the continuity correction. These again are integers, so I will just reduce it by 0.5. So if I reduce it by 0.5, this will be 0.5.
Why did you reduce and not increase in this case? Oh, because
I want to
it's
include,
greater.
yeah. So including 65, so we'll be lower. Right. All right. Probability X minus the probability that X minus 50 over square root of 5 is equal to 65 minus 50 over 5. And at this point, I say this is approximately the standard normal is greater than or equal to, to 64. So that's 14.5 divided by 5. Probability that so it's 1 minus the probability that C is less than or equal to 2.5 divided by 5. Choose 10. So 1 minus 5, 2.9. Okay.
I'm sorry, why is it 5?
Yeah, just a second. So 1 minus point.
Oh, no, thank you.
I was going to correct. That's attention span. Yeah, 5, yeah, that was the square root of 25.
Thank you.
Yeah, what was 5, 2.9? It was 0.99 something.
81.
9981. Yeah. So 1 minus 0.9981 is the answer. So what do you get that to be?
Why do we change the greater than to less than?
1 minus.
0.001.
Yeah, but we want less than because I want to use this table. And the table contains only these values. What are these values? These are the probability that X is less than or equal to X. So that's why I always want to convert it into probability of X. Z is less than or equal to X. So I always want to write my problem in terms of probability Z less than or equal to X. Because that is 5X and 5X is in my table. Alright, so what do you get this value to be?
0.0019.
0.0019. So actually there's a very small probability that the nutritionist will endorse it if it doesn't affect diet. So that's pretty good.
Just
Huh?
I found out that apparently I can do summations on my calculator, so
Oh,
summation is 0.01759.
0.0010, oh, that's pretty close to this.
Yeah.
So you see the normal approximation is pretty good. So, so you see that actually there's, if this has no effect, there's only a 50-50 chance that your cholesterol goes up, so that means it has no effect, then actually the nutritionist will endorse it with a very small probability that, there's a very small probability that the nutritionist will endorse it. So clearly then there must be some evidence that, I mean, so clearly if it doesn't affect diet, it will not get endorsed. If your criteria is 65% or more, the people have to show lower cholesterol.
If that 65 got closer and closer to 50,
yeah, then there would be a high probability that
probably
you
come
get
to like a
endorsed.
half.
Right, yeah, then it gets close to a half, right? Because, so that's what, if you move it above the mean, if it's very close to the mean, then yes, you expect with half probability that it should be greater than or equal to the mean. But the minute you move even like 15 away from the mean in this problem, out of 100, so yeah, so that's not too bad. So if you require, so clearly if you require 75% of the people have to show lower cholesterol, I mean, actually 65 is good enough. You don't need to go to 75 because this is already the probability rounds up to 0.
Of course, the problem is that it's really not a 50-50 about their levels going up and down because like other stuff changes too.
Well, other stuff we're saying, assuming everything else stays constant.
Right, which is just impossible.
Yeah, but that's what people in biology. Oh, any biologists here? Yeah. So I have friends in nutritional biology, and I always find it strange is that they say that they can verify something up to like a certain degree of confidence. You know, that experiments. It's like for me, an experiment is just checking one particular outcome from a probability distribution. So you will never actually know the truth from an experiment. I mean, for me, unless you prove it mathematically, it's not true. and I've had these arguments with biologists who say, no, experiments are the way to go. And I'm like, no, it's not. There's always a probability of error. So, yeah, for absolute truth, you've got to stick with maths.
Am I reading that correctly as
Yeah.
the 65 or more would have been 3 standard deviations away from the mean?
So a standard deviation was how much here? Was 5, so 15? Yeah,
Okay.
3 standard. Oh yeah,
It
so
makes
actually,
sense
yeah,
that
it
you
makes
know.
sense, yeah.
Okay.
Our standard deviation was only 5, right? Yeah, okay, yeah. Yeah, so 3 standard deviations we already know was, it gives you a very small probability. I think we calculated that last time, yeah. So that's already pretty far. So I think that could be like a standard test. Well, if you do some statistics, you come up with, you would usually try and check like, if you want your criteria to be like very stringent for testing stuff, you would check that, you know, if up to like 3 standard deviations away was also give you like a high probability, then okay, then, I mean, it has to be a low probability. So, so yeah, so they do some statistics to figure out what should the cutoff level be that you look at.